We have now looked at the bivariate distribution in the discrete case. What I'm going to do next is to talk about the bivariate distribution in the continuous case, right? So as you can see in the title, I'm talking about bivariate and multivariate distributions, but I'm only discussing bivariate distributions here because they're easier to conceptualize and to draw graphically. But the ideas that I'm presenting here will generalize to any number of random variables, okay? And later on, when we do Bayesian data analysis, we'll be working very intensively with multivariate distributions, right? So they will become our bread and butter activity. Okay, so let's think about bivariate distributions in the continuous case, right? So now imagine a situation where you have two random variables, just like I showed last time in the discrete case, but this time they're coming from some normal distribution. So just to be concrete, let me say that they come from a standard normal distribution with mean 0 and standard deviation 1, okay? Let's also assume that there is some correlation between these two. Okay, so for a real life example which doesn't involve the standard normal, you can think of height and weight, right? If you measure each person's height and weight, these will tend to be positively correlated with each other, right? Because the taller a person is, the heavier they might be. Okay, so of course there will be variation, but in general that there might be a positive tendency, you know, a positive correlation. So that's what I mean by correlation here informally. And so what I'm saying here is that you've got two random variables. In this case, the standard normal, both of them are standard normals, but they have a positive correlation or negative or some correlation between them, which I'm calling rho xy. So I generally put the subscripts, you know, for the random variables that I'm talking about. When I'm talking about the correlation between two random variables, I will reference them with the subscripts, right? So that it's clear which random variables I'm talking about when I talk about their correlation, right? Because they can be more than two. That's why this is necessary. But sometimes it's clear from context, and so sometimes you'll just see rho instead of the subscript. But that doesn't matter because you know from context which correlation we are talking about. So in this case, the example I'm considering here, right, we are going to describe a bivariate distribution now, right? So we're going to describe a probability density function for a bivariate distribution, taking into account the means of the two random variables, standard deviations of the two random variables, just like in the standard normal case that we saw earlier. But the new thing now is that we have a correlation between, potentially, we have a correlation between the two random variables. So we need to include that in the probability density function equation to describe, you know, the relationship, the way that these data are going to be generated with that particular correlation. Now, what we do in statistics for such bivariate distributions is that we will describe the standard deviation and correlation in a very special matrix form, which is called a variance covariance matrix. Okay, so in this particular case, because we have two random variables, right, we have a 2 by 2 variance covariance matrix. If we had three random variables, we would have a 3 by 3 and so on, right? So this of course depends, the dimensions of the matrix will depend on the number of random variables you have, but today I'm only considering the bivariate case, just to keep the story tractable, okay? So we have a 2 by 2 variance covariance matrix, and what does this look like? So I will show you now. So the variance covariance matrix is generally written in statistics with a big sigma. Okay, so of course now this is confusing because this is very similar to the summation symbol, but from context you will know that we are not talking about summation here, but about the variance covariance matrix. So in the bivariate case, the variance covariance matrix has a very specific form. The diagonals of the variance covariance matrix will contain the variances, not the standard deviations, the variances of each of those two random variables, so the square of the standard deviation, and the off diagonals. Okay, so this is one off diagonal, this is the other off diagonal. The off diagonal contains the so-called covariance between the two random variables. Now, if you've never heard about covariance, intuitively you can think of it like this. So if there's a positive correlation, if one random variable increases in magnitude, the other one also increases in magnitude. So that would be a positive correlation. So that we would call the covariance would be positive, right? When one increases, the other also increases. And you can imagine the situation where it's the opposite, when correlation is negative, right? So the definition of covariance is written here. You don't really need to know more than this, actually, for the purpose of our course here. But of course, there's more detail in the lecture notes, and you can look up textbooks also, of course, which explain more details. But this is what we need to know for our current purposes, okay? So the off diagonals have the covariances, which is defined as the correlation multiplied with the two standard deviations of the two random variables, okay? So once we know these three numbers, the variance of x, the variance of y, or rather the standard deviations, and then the correlation, we can figure out this variance covariance matrix, right? So this is very useful because now we can describe completely how these two random variables are jointly distributed. Remember the discrete case I showed you earlier? There we had discrete values, now we have continuous values, but we can still talk about the joint distribution of continuous values. And the way we write this in statistics is that if you have two random variables, x and y, we are going to say that these two random variables have as PDFs a two-dimensional normal distribution, right? That's what that subscript under the n means. The means of those two distributions, I'm just assuming is 0 because I'm talking about the standard normal in my example, and some variance covariance matrix. So the form of this matrix will be as I just described earlier. If it's the standard normal, what would sigma squared x and sigma squared y be? These would be 1, right? Because the standard deviation is 1. And so whatever the correlation is what you would get in the off diagonals here, right? For the standard normal case that I'm discussing, right? So this is called the joint PDF of these two random variables, and you will often see it written like this with f, again the f for the PDF, and with the subscripts which actually specify which random variables we're talking about. These uppercase x's and y's actually refer to the abstract object, you know, the random variable, and the lowercase x's and y's are referring to specific, you know, data that you might get. Okay? So I will always make this distinction between capital x and lowercase x. Capital X means the abstract random variable, and lowercase x means a particular data point or data set that we have. Okay? All right, so this is the joint probability density function of this particular example. What does it look like, right? So it's very important, I have said this before, to get a graphical intuition for all of these abstract mathematical ideas. So they feel very dry and unintuitive if you look at them as equations, but it's much easier to visualize them as figures, right, as graphics, and this will help you understand what's going on here. So I'm going to show you all this, right? So one important property of this joint probability density function has to be, right, for it to be a proper probability density function, it has to be that the area under the curve has to sum to 1. Right? Now this joint probability density function is going to be a cube. It's going to be a kind of cone, not a cube, but a cone. And I'm going to show you the shape in a few seconds. But this cone, the area under the curve, contains the probabilities of all possible outcomes. So if you think about all the possible outcomes in x and y, the total area under the curve has to sum to 1, right? So that otherwise it's not a proper probability density function, right? Okay, so formally, right now I'm just showing you the formal story, but I'm going to show you the graphical intuition. Then you'll see that these ideas are not actually very complex. They do look complex when you look at these equations, but they're not really, right? So what we are saying here, this statement in English is just saying that given this joint probability density function, the total area under the curve, right, I'm summing up over x and y, is going to be 1. That's what I just said a few seconds ago, right? And we'll just visualize this in a second, right? And I could also write the cumulative distribution function now, right? I could ask what is the joint probability of observing a value like u for the x random variable and v for the y random variable, or something less than that, right? In this three-dimensional space. I can also ask that, and that probability can also be computed, right, using the CDF by just carrying out the integral. So remember, when we were doing the CDF earlier, we were summing up things, right, in one dimension, because we had a univariate distribution. Now we have a bivariate distribution, so that's why there are two integrals. There's conceptually nothing new going on here, right? All that's changed is that the number of variables has changed, okay? So luckily, we don't have to do any of this math when we are actually doing analysis. It's just important to understand what it means to have a joint distribution, okay? So we can also compute, just like in the discrete case that I showed you earlier, we can also compute the marginal distributions, right? So we can figure out the marginal distribution of the random variable x by summing over the y variable, right? That's what I had done earlier with the discrete case in the previous lecture. And similarly, you can do the same thing for the marginal distribution of y. Right? So this is nothing new here, because this, all we have done is we replaced the summation symbol in the discrete case with the integral, nothing more, right? So now for the visualization. So this should help you understand what we are talking about when we are talking about this example of two standard normal variables, right, x and y. These are perhaps correlated, right, or perhaps not. So what I'm showing you now on the right hand side here, I'm showing you the cone that I was talking about earlier, right? This cone here describes the joint probability density function of a bivariate distribution of the type I'm discussing. This picture here shows you the contour plot from above. So it's like a geographical plot showing you the density, you know, of the points that are making up this cone here, right? So you're looking at this cone from above here, right? And what I'm showing you at in this lower part of this plot here is the joint cumulative density function, you know, of this random variable. So what this joint cumulative density function, which will go up to 1, by the way, right, is going to tell me the probability of finding some value like u for x and v for y, or some value less than that, right? Just like in the standard case that we learned about earlier, right? So it's all generalizing. So what's another interesting thing you should notice here is that the correlation that I've specified here is 0. And what that means is that this cone is going to be perfectly symmetrical, right? And the reason for that is that there's absolutely no relationship between x and y, because correlation is 0 here, right? When correlation is 0, you will see this characteristic spreading around of the data points, you know, around the center points, around the means of the two random variables. In this case, the mean is 0 and 0 here, right? So you see a consistent spreading around of data around this, and there is no correlation here. But what would happen if correlation were positive? What would this contour plot look like? Just think about that before you look at the next part of my lecture, right? Maybe you want to pause the lecture and just think about it for a second. What would this contour plot look like if there was a positive correlation between x and y? Okay. So what would happen if it's a negative correlation, right? A negative correlation would involve when x is going up, y will be going down. So the contour plot will look like this, right? There will be this characteristics, this angling of this contour plot, right, when you've got a negative correlation. And the shape of this cone will also shift, right? You can imagine this looking at this contour plot from the side, and you would see the cone looking like this. This is the cumulative distribution function here. Now what would happen now? The question that I asked you, what would happen if the correlation is positive, right? What would this contour plot look like, right? The contour plot is going to shift in its directionality, right? It's going to get squeezed in this positive direction, and what this means is that when x is increasing, now y is also increasing. See, the covariance is positive now, right? And the correlation is of course positive then, right? And so the shape of this contour plot will also of this PDF, joint PDF, will also change, right? So that's basically the main, you know, issue that I wanted to get across to you here. In the continuous case, just like in the discrete case, we've got marginal and conditional distributions that we can compute, and we've got the joint probability density function that will be described in the case of the normal distributions that we'll work with so frequently, right, will be described in terms of the means and the variance covariance matrix. These are very important ideas that we will need when we are working with, especially with hierarchical models. Okay. All right, so one thing I want to show you now is something very cool. you can actually get a very good intuition for what a bivariate distribution will look like by just simulating data. This is why I taught you all about those R-norm functions and so on, right? You need this functionality to be able to generate simulated data to develop intuitions about what you're working on, right? The problem you're working on. So what I first do here is I've created a variance covariance matrix. This is a 2 by 2 matrix, right? And what's happening in this matrix is that I've got in the first row, first column, I've got 5 squared, which is the variance of the first random variable. I just decided on something, right? And here I've got 10 squared, which is the variance of the second random variable. And on the off diagonals, I've got the covariances, and I'm assuming a correlation of 0.6. So what does this actually mean, right? So you just want you to just take a look at how I would write this out if I wanted to explain this mathematically, right? So I've got a 2 by 2 variance covariance matrix, right? And so I've got 5 squared here. This is the variance for the first random variable, and I've got 10 squared here, and I'm assuming a correlation of 0.6 here. I'm just assuming this. Why? I'm assuming these numbers because I just want to generate some simulated data. So I have to choose some parameter values to do that, right? So sigma x is 5, right? And sigma y is 10. Right? In real life data analysis, of course, you do not have the luxury of knowing what these parameters are. The whole game is about estimating these parameters, but we'll get to that soon. Right now, we're trying to understand how to generate data, okay? Simulate data. So on the off diagonals, I'm going to write this correlation, right? Rho times sigma x times sigma y, right? What would that be? It would be 0.6 times, I'll write it like this, 5 times 10, right? So this number would be the same number here and here. So I wrote the formula on the top and the actual numbers on the bottom. So this would be my variance covariance matrix, which I'm writing as big sigma, right? This is the big sigma here. And what I'm showing you here is that I created that in R. And then what I do is I use this mass library, which contains a multivariate R norm function, right? If you remember, in the univariate case, we had the R norm function for generating simulated data. We can simulate fake data in a multivariate situation, in this case a bivariate situation. And what I'm doing now is that I'm using the mass library to run this function, the MVR norm function. I'm generating 100 data points, so a set of 100 data points. That means a total number of 200 data points from a distribution with means 0 and 0. So this is how I'm specifying how many dimensions I have in this distribution. It's a bivariate distribution. If I had written 0, 0, and another mean here, for example 0, if I had written 3 zeros here, then I would be talking about a distribution with 3 random variables. So that would be a multivariate distribution. And then the sigma would have to change also, right? The sigma is a 2 by 2 variance covariance matrix. Why? Because I have 2 random variables right now. But if I had 3, then I would have to write a 3 by 3 variance covariance matrix. Okay. So coming back to this case of 2 random variables, I'd specify my means, I specify my sigmas, and I strongly advise you to play with this a little bit, right? Change the means, change the sigmas and the correlations, and see what happens. Okay. So what I do now is I save the results of this simulation in this matrix U, and what I've got here is 100 rows and 2 columns. Why do I have 2 columns? Because I have 2 random variables. I've generated random data from the random variable x here and from y here, right? And so what's cool here is that I specified a correlation of 0.6 between these two, right? If you just look at these 3 data points, you're not really clear on what's going to go on, like if I look at the correlation. But if I plot these data points, these are 100 data points from the x random variable and 100 from the y random variable, you see this positive correlation here. So if you just fool around with this code a bit and change this plus 0.6 to minus 0.6, right? And run the code again, run all this code again, you will find that the data is now going to have this negative, angling that you're seeing. You're seeing a positive angling here, you'd see a negative angling here. If you, on the other hand, if you set this correlation to 0, you should try this out, right? Try it out at home. Set all the correlations here, these 2 correlations here to 0 on the off diagonals. What you will then get when you generate data is a blob, a symmetric blob, right? That is basically just showing you that there is no correlation between the two random variables. Okay, right. So usually, when I teach this material that I have just presented on random variables and distribution and so on, somebody always complains to me that why are you teaching us all this theoretical nonsense, right? Why can't we just do data analysis right away, right? And in fact, that's how I learned data analysis too. As a graduate student at Ohio State, I was just like thrown into the middle of things, just given the data and told what commands to run and analyze my data. Now, the problem with doing that kind of Mickey Mouse data analysis is that you have no idea what's going on behind the formulas that you're using in your R code or whatever, right? What I'm trying to do is I'm trying to make sure that you fully understand what the assumptions are of all the models that we're going to build. Because later on, when we build more complex models, the assumptions will pile up, right? And you want to be sure that you understand what you have assumed is producing the data, right? Often these assumptions are not reasonable, right? And you will see later on in the book that the story can become incredibly complicated. And there you have to be very clear about what multivariate distributions you're assuming and what generative process you're assuming for the data. That is why it is so important to know what a probability mass function is, what a probability density function is, what a marginal distribution is, what's a conditional distribution, how do these DPQR functions work, right? We need those because when we start thinking about prior distributions, which I will explain very soon, when we start visualizing prior distributions to try to understand what we think plausible values will be for the parameters, we need to be able to use these DPQR functions to work out what we assume about the priors, right? So this is a very important skill that I hope to convey in this course. And that's why I made you suffer through all this technical detail, right? This is the preparation that we need to fully understand what we are doing when we are actually carrying out data analysis, right? So in my work as a psycholinguist, I repeatedly see published papers where even a simple one sample t-test is not done correctly. This happens even today, right? And it's going to happen forever. And the reason for that is that the foundations are very shaky. Among the people, for example, in psychology and in linguistics, it happens quite often that the foundational ideas are not there because people just were not willing to spend 1 week thinking about probability density functions and probability mass functions, right? And then you pay the price for that shaky foundation down the road. This is a very expensive price to pay if you're trying to do science. So why not just spend a week and figure out all these basic ideas? There's really not much. It just involved simple addition, maybe division at one point, and that was it, right? And some graphical intuition is all you need. And once you understand these issues, it'll be much easier to understand how Bayesian modeling works and even how frequent test modeling works. I mean, all of statistics is based on the ideas that I just presented to you. So what we're going to do next, after finishing this hard first week, is we are going to now get our hands dirty with Bayesian modeling. I'm going to show you some really cool, simple Bayesian models that you can do on a piece of paper without any computer, and then we will move on to much more complex models involving computational tools.